It's high noon, and on xChips Daily today we're going to talk about the A801. There's going to be some technical talk here, and the chip itself, as we have here, is of course interesting, but it's the details behind the chips and some understanding about encryption and electronic signing that's going to be the talk today. I apologize up front if the sound quality is not the best, but I've been pushed outside for the day's broadcast, and I didn't want to necessarily cancel it. So, sorry, here we have on the right hand side the A801, and that chip that sits in the middle there is called ATEC 508A. Next to it is A802, which have the newer ATEC 608A. Now the A802 is a prototype, it's not been produced, we're not selling yet and all that kind of stuff. And what we're probably going to do is that we're going to just upgrade the A801 to the newer 608 chip. It's backwards compatible, so there's no reason to necessarily have both of them. So the A801, as we say on our own website, it's a SHH-256 hardware encryption chip. So what does it do? Well, mainly two things. It does signature, electronic signature, and it do encryption. The A802, or let's rather call it the ATEC 608A, can do the same. As I said, it was backwards compatible, but it can also be used for secure boot, and there's a number of newer security standards. Obviously, when it comes to security, things get updated all the time. So there's new protocols as the older protocols get easier and easier to hack, simply because the computer power is getting better and better. And obviously, when the computer power gets better and better, well, we have to have stronger protocols, but we also have the computer power to use the stronger protocols. So that's the reason why this thing here is of course gonna continue. So what does this mean, this signature and encryption? Well, you're in luck. For today I'm gonna talk about something that I actually know a little bit about. So back 18 years ago, I wrote an article about signing and encryption in Visual Basic, and it's actually the same kind of stuff I'm going to talk about today. I even have a patent from 1999, so they last 20 years. So this one, oops, of course that kind of stuff have to happen. So I have a patent here, and it's from 1999 and it's expired, but it's actually a patent that relates to this encryption here, because while today we can use like something like a chip like A801 or A802, back when I wrote about this thing here, you would put it in a smart card, like similar to a SIM card, just the big ones. Maybe you guys who have DSTV kind of like have this kind of like authentication card that's the same size as a credit card. So this thing here was a reader for being able to have this functionality on a smart card. So I need to talk about asymmetric cryptography, because this is actually important to understand this thing here, and understand when you start coding against the A801, then what does a different thing means, and when you understand the background of this thing here, it's going to be much easier to program it. So as always, we have our two guests in this little program here. We have Alice and we have Bob. So Alice are making two keys. Actually, she makes a set of keys. They're very special keys that she make here. And of course, this is all electronically. But you know, when we talk about the key, it helps to kind of like visualize it a little bit. Unfortunately, what we can do electronically here, we can't do necessarily in real life. I haven't seen it. Might be there, but I'll come back to that. So you have a set of keys made. In this case Alice, and Bob will also have a key like that made. This is the most important. If you take anything away from this half an hour talk here, this line is the most important. Whatever you lock with the one key, you can only unlock with the other key. So imagine a lock where it doesn't actually matter what keys you use from anybody in the world. It has, you can use Bob's keys, Alice's keys, my keys, whatever it is. So this lock here can take anybody's keys. But when you lock it with Alice's public key, you can only unlock it with Alice's private key. And if you lock it with Alice's private key, you can only unlock it with Alice's public key. So this is the important part. You can't lock something with a private key and then unlock it with a private key also. The private key you keep for yourself, never to be shared with anyone. So this is of course one of the things that's going to be important later on, because how do you make sure that you keep your private key private? And this is where the AH01 comes in. You need to make sure that you can keep your private key private, that it doesn't get compromised under any circumstances. Imagine your PIN code on your ATM card, smart card, whatever, credit card that you put into an ATM. This private key is similar to this PIN code. And then you have a public key, and that you can share to the entire world. Scream it out there on Facebook, Twitter, put it in a newspaper, whatever. Everybody can have it. It's absolutely free to use. Everybody can have it. Remember, if anybody uses it to lock something, they can only unlock it with a private key. If anybody unlocks something with it, then it will work if it was locked with a private key, and then it's okay too, and I will tell you why just now. So let's start with a simple use, the signature. So here we have a little diagram here, and we have Alice who locks a message, let's say inside a box. This kind of like, visualize it's a box where there's a lock on this box here. This lock is this special lock that can take any keys, but when you start locking it with a set of keys, then only the opposite of this set of keys can open it. So Alice locks a message in a box with her private key. So now it's locked. Anybody can open it, because remember, everybody have access to the public key. So in this case, Bob unlocks it with Alice's public key, and then he knows that it comes from Alice, because Alice is the only one who has the private key. So when Bob opens it with the public key, he knows it was locked with the private key. It cannot be locked with the public key and opened with the public key. Okay? So because of this thing here, then anybody who unlocks this message with the public key, anybody can unlock this thing with the public key. So it's not encrypted. This is, anybody can see this message. So even though that you unlock it like this thing here, then everybody can, it's kind of like encrypted, but because you unlock the whole message with the public key and anybody can do it, you don't see it encrypted. But because we know it comes from Alice, we see it signed. So if you anytime see like, on your email that you have signed and get something that's signed, it simply just means that their email system have a facility where they can put a private key on an email and lock it with an email. So when you then get it in your email system, it will come up, say, electronic signed or something like that. Because your email system will go out there and find the public key somewhere and open it and can see that this is from this person. So let's take another simple use, the simple version of encryption. Now we just do it the other way around with the keys. So Bob locks a message in that box with Alice's public key. Now only Alice can open it because he used Alice's public key. Alice unlocks it with a private key, and if that worked, if she indeed could open it, then it has been decrypted. But anybody could have locked this message. Remember that. I mean, Bob says he have locked this thing here with Alice's public key. But how do we know it's Bob who did it? It could be anybody who logged it with public key. The only thing we know is that only Alice can see the contents of this thing here. So by Alice opening this thing here, she knows that whoever sent this thing here, the data haven't been compromised. Data is the same. And remember, many times it's not necessarily just whether people have seen the data inside. It's not like necessarily a list of all the spies somewhere, okay? It can just be that it's a computer program and you want to know that that computer program has not been modified. Somebody haven't put a virus on it or something like that. So when you open it with Alice's public key, when you open this thing here that was sent to you this way here, then you know this program that was sent to you like this thing here has not been modified. But you still don't know who it is from. And it's encrypted. Nobody else can see this program. So I will use the signature, and this is how it works. If you sometimes see that people say, here's the MD5 key or SAH256 hash, they call it, then this is actually a compressed version, and I'll come back to that, of the entire program. So what you can do is you can run a hash on your program and it comes out and make a shorter one, and therefore you know that the program has not been modified. But let's continue here on this side here. So I hope you understand the difference here is that with the signature, we know it came from Alice, but everybody could see it. And with this encryption here, we know Alice is the only one who can open it, but we don't know actually who sent it. We just know whoever sent it to us want to make sure that nobody else saw it. So here's the secure way, and that is that you combine, and this is the important part because this is how the top security works everywhere, okay? Alice locks her message in a box with her private key, and after that, she then locks that box inside another box with Bob's public key. Of course, electronically, so you don't have a set of boxes like I have here in the picture, but that's how you can kind of like imagine it. So Bob now have to unlock it with his private key. That way, when Alice locked it with Bob's public key, nobody else could open it. Only Bob could open it. So the other box was locked with a public key, so it can only be opened with the guy who owns the private key. So that's Bob. So he opened with the private key. And then inside there's a box that's locked by Alice's private key. So when he unlocks it with his public key, then we know that that message was encrypted and it was coming from Alice and was sent to Bob. Now, notice in this process here that, you know, normally in the old days when you kind of like thought about encryption and things like that, is that you had like some key and then you have to give that key to somebody else. And when you have to give that key to someone else, how do you give them the key? You know, do you send an email? Well, then somebody can actually get hold of the key. The solution here with this technology here is that you make a set of keys and Alice makes a set of keys, Bob makes a set of keys, and I don't have to share any keys. I mean, the public keys is like everybody can use it. But if you just had one key that can open and lock things, then you need, you can, that key can be copied, because when you have to send that key from Alice to Bob and say, here, I'm sending you a message, I encrypted the whole thing, and the key to open it is this key here, then somebody could intercept that email. It's little if you get like a credit card and you get the PIN code in the same envelope. You get it in the other envelope. It's not really the same thing, because hey, if that comes at the same time as the credit card, then you know people could intercept that. So because the box could only be opened, because Bob could only open the small box and Alice's public key, he know the message from Alice. Okay, so that's the concept of asymmetric cryptography. there is a, you know, when you see, for example, a website and it's HTTPS, we call it SSL, Secure Socket Layer, or TLS. There's like a couple of different terms for it. But when you have a website where there's a little lock up there and it's a HTTPS, the way it works is that the bank, let's say it's a bank, they send you their public key. That the browser deals with that. You not necessarily have to do anything, but they send you their public key. Actually, when you have certificates and all that kind of stuff, the public key is part of that certificate. And if you go into details on this thing here, there's kind of like a repositories on certificates, but it's another repositories and other certificates and so on. There's a whole structure out there. And when you come out of the browser, you just tell who's the top kind of like libraries of keys, and that's where you go and find the key. So they will send a message to you. You will go and find a key and a public key. Now, when they send a message to you, they send out a private key, and you can then open it with a public key. The only thing you know is it came from the bank, but everybody could see the data. So that's the reason why, for example, if they say you use this credit card, they're not going to show you the whole credit card. Even a secure website, they're only going to show you maybe the last 4 digits. It's because if they send the whole credit card back, anybody can see it. So the communication from the bank or a payment solution or whatever to you are signed, but it's not encrypted. We know it comes from the bank, but anybody can see that data. However, when you then do your payment, or when you do fill in the credit card, then the browser locks it with a public key, and only the payment solution provider can see what you locked there. So they have the private key, their own private key. And that way, data is signed when it comes to you, so you know it comes from the bank, which is many times the most important. And of course, all the data that you see on a website from the bank, just understand that everybody else can see this thing here. So yes, so this is the way a website works, and there is certain websites where they ask you to create your own certificate, what's called a client certificate. So you have to create that and store it and all that kind of stuff. And when you have that, then you can have a two-way encrypted communication, but it's not normally used. None of you have probably ever done any of that kind of stuff, but you can. And the same technology you can also do in an email. You can make yourself a key set. And sorry, I just have to check here. Okay, so that's cool. So you have a yeah, in your email, you when you get this signed, it's because somebody have actually created themselves a certificate, and there's a public certificate. Remember, if you do make a private certificate, of course you can do that with a software called OpenSSL and things like that, but then nobody have access to that public key, and it's not verified as necessarily you. So what happened is that you can go to like a certificate provider and say, listen, I want to have a secure email signature, and then they verify you are indeed who you are. I did that long time ago with Thought, which was this thing here that Shuttleworth owned many years ago, and I got like an electronic signature. Obviously, because I wrote all these articles and things like that, I needed to figure out how all that worked. None of us use it. We send an email. The receiver is not using any kind of encryption. The other way is not. So, you know, whenever you send an email, it's normally not encrypted any of the ways. Now I want to get into the xChip here. So what if Alice is an XK01 and Bob is Microsoft Azure? So we need to store this private key in a very private place. Okay, so here it comes in. We have this private key, and XK01 need to have, if we want to do this secure communication, we on XKR1 have to have a private key. If we just want to make sure that we send our data from our XKR1 to Azure, then Microsoft Azure can send us, and that's how it happens today, they can send us a public key, and that you sometimes when you have to download certificates and things like that when you program, then you are in that situation. So they send you their public key, you take your data, you wrap in this public key, and you send it to Microsoft Azure. And they now know that nobody else between your XKR1 and Azure could read the data. But they don't know it from you, because we only did the encryption. We didn't do the signature because we didn't use our own keys here. So in many cases that is fine, and that's the reason why we can upload to Azure and Google and a number of different places today with the CW1, especially with the CW2. We just have to go through the nonsense of getting certificates and loaded them in and all that, and the guys who are programming that know what I mean when I say this nonsense here. It's not necessarily easy. But you have the certificate, you get the certificate, and in certain instances what you will do is you will get the certificate at programming point, and it's only able to upload to one server because you only stored one certificate on your CW1 or CW2. So, but let's say for example that your server now you want to make sure that Azure knows that that data came from you. You want to avoid what's called man-in-the-middle attack. You want to make sure that it's encrypted both ways and signed and everything. Obviously, the way it works with Microsoft today is that they issue you like an API key or some key, and inside your code that you send to Microsoft Azure, there is this key, so they know it's from you, unless you screw it up and share that key with somebody else. So, and you probably do that because the software you put on XKR1, everybody can read. You can take the software that you put on a microprocessor that you can lift off. I mean, it's not like necessarily easy for everyone, but you can take, for example, our IPR1, and you can read the code of the CW1. It's compiled, so you have to do something called disassembling, but any starter hacker will know how to do that and go through the code and find your key that you're using to communicate to Microsoft. So if you do it this way here, while with kind of like just a simple way with the encryption like this thing here, you have your credentials, your authentication credentials stored in the memory on the CW1 or CW2. Just remember, those devices are not secure. They don't have a secure area or anything like that. So that's where the A8s come in. It have a secure storage that you can't get. Once you put it in there, you can't read it. The other thing is that once you put it in there and you can't read it, you also want to make sure that you don't need to show this private key when you encrypt. So for example, the way it works is that when you take your ATM, like credit card, and put it into an ATM, or you know, pay within a garage, and you put your PIN code in, it's going to show us the private key. So why this security here? Is the CPU in the A801 fast enough? So let me just take this in. So obviously this is a, you know, you look at the A801 and say, wow, this is a very little CPU, can that do all this encryption? So what many times happen is that, for example, if it's a signature, what you will do is that you will not encrypt the whole message. So what you will do is that you will take the message. So let's say this is the JSON that, like I explained, I haven't explained yet, but the JSON is kind of like the data format that we sometimes use. Now let's say that's 500 characters long. What you can do is you can take and say, I'm gonna do a hash. What it does is that it kind of like compresses it. It's not really the way it works, because it can't uncompress it and then generate the code. But what it does is that it kind of like calculates a a check digit, if you can call it like that. It takes that entire code and it kind of like make it into like a string of numbers that's maybe like, you know, 20 character long or something like that. So you have this 1,000 character message you want to send, and you have this hash algorithm, and what it does is that it makes this string that's 20 character long, and then what you do is that then you encrypt that one with your private key. When then the receiver get on the other end, they get the message and they get this hash and they have the public key, and what they do is that they then decrypt the hash, this 20 character, and now they get the 20 character in clean text, and now they have the hash, and then they perform the same calculation. They take the code and say give me a hash out of that, and now they compare the two hash values, and therefore you don't have to encrypt the entire message, you just encrypt a hash out of this in here. I know this is like a little bit deep, and of course I can try to explain that on a later stage, but I think by now I probably lost enough people here. So could we not do that in a CW1 and CW2 call? And sorry, I should have done something to remove this splash here. So they're not secure. That's what I said before. You can actually offload the data of the CW1 and CW2. So you don't want to do this thing here on these modules. And of course there's a lot who does it. I mean, CW1 and CW2 is being used for this thing here, but that's a fake security. People have this little ally leaving the key underneath the mat, you know, or like the key for your car in the visor. You know, people know it's there, they can open it and that kind of stuff. If people see there's an A801 in your circuit, they're walking away. They're not going to try to hack that device. And of course, one of the important things here is that we talk about the XK1 as being this security product here, but that just shows the temperature. But what if this is actually the other way around? What if this is like your garage door opener, or the opener to the office building? So what it says underneath this splash here is that imagine that you have a CW1 that can open and close the main door to your office, to an office place. So you get access to it in a normal environment, you know, normal office hours, and then you go and you clone